So we prove this useful theorem. So assume the orientation vector is the same direction of our cross product. Therefore, n is the normalization of the vector. Thus, our integral is the integral the usual integral of the inner product function. So this usual integral can be transformed into double integral over the domain D. How to transform? That is, you take the substituting the parametrization, then multiplying RU cross RV, the norm of RU cross RV, and then du dv. This is the formula for computing. Actually, this is by the definition of surface integral. Surface integral is defined by a double integral using the parametrization of the surface. Okay. Now, substituting the n here, you will see that the denominator of n and the norm of RU cross RV here cancel. Okay, so this gives us then inner product, which here inner product which n, but the denominator of n, that is the norm of RU cross RV, cancel. Therefore, we only have RU cross RV, then du dv. So this completes the proof. Quite easy. Okay. So we consider an example. We consider an example of computing flux integral. For the integral of this form, that is from an integral, the integral of a real valued function, but with respect to the project surface element. dz dx is the projection of d sigma to the xz plane. So maybe we should call this the project integral. Maybe this is a proper name, a suitable name for this kind of integral. So we have surface integral, flux integral, and the project integral. Okay. Now, project integral is essentially a special case of flux integral. Therefore, this theorem for computing flux integral is applies. Okay. So, for example, a particular form of this result, taking f for the particular form, taking f to be p0, 0, we see that a particular case of the result is p dy dz is positive, negative, d p r u v. So that is f is p0, 0. So the inner product of f and this normal vector is p multiplying the first component of p minus p multiplying the first component of the cross product RU cross RV. The first component of that is YZ. uv. Okay, then du dv. So this relative equality is a special case for the equality in the theorem, which the vector field capital F taken p0, 0. So the cross product vanishes. Because the last two components of capital F is 0, therefore the inner product is simply P multiplying the first component of the cross product. But the first component of the cross product is yz, which is the Jacobian determinant of yz with respect to uv. So this last equality for the project integral is also quite intuitive. You can imagine concerning the duv and the duv here, you still have dy dz. That is what we want to compute, the integral with respect to dy dz. Okay. Of course, this is just an imagination. Now we compute a flux integral. Actually, we compute a project integral. That is sufficient to represent the idea. So this is the upper unit sphere oriented upward. So this is the x, y, z, and our hemisphere upward. That is n. And we will compute the integral I equal this surface with that orientation x cubed dy dz. We will compute this integral. So the first step is to take an parametrization. It is well known that the parametrization can be taken by R defined on the unit disk. That is the projection of this surface in xy plane. And the square root of 1 minus x squared minus y squared. Okay. So we need to compute the partial derivative with respect to x. That is 1, 0, minus x over 1 minus x squared minus y squared square root. Similarly, ry is 0, 1, minus y over 1 minus x squared minus y squared. And their cross product is the determinant of 1, 0, minus x, 1 minus x squared minus y squared, 0, 1, minus x over 1 minus x squared minus y squared. Okay. And here is the I, J, K. So expand this, you will see that this is x, 1 minus x squared minus y squared, y, 1 minus x squared minus y squared, and the last component is 1. So because the The third is 1. The third component of this cross product is 1. The cross product is a normal vector to the hemisphere. But as a normal vector, it can point upward or downward. We don't know. How to determine whether this Rx cross Ry as a normal vector it point upward or downward? You observe its third component. The third component is 1, which is positive. Therefore, this normal vector point upward. The same orientation with the surface. That is Rx cross Ry has the same direction. Which the orientation vector n. Okay, so this is the how to determine the sign positive or negative in our theorem, in applying our theorem, or in applying our result in the last line of this page. This is the method. Okay, so we know that when we transform this project integral into a double integral, we need to take positive sign. Now, taking positive sign, our integral I is x cubed. So we can using the I don't have enough space to write here. I should go to next page. Our I, maybe I don't read. I is x cubed dy dz. That is B1. We're using our formula here to convert the project integral into a double integral. Okay, so this is the domain is B1. The function is x cubed, and multiplying the first component of the cross product, that is x 1 minus x squared minus y squared, then dx dy. So the project integral has been transformed into a double integral. What's this? This is the first component of the cross product. That is precisely the Jacobian determinant of yz with respect to uv, with respect to xy. Okay, so you should be very careful about this equality. The sign in front of the double integral is positive sign, we have explained. And the ingredient of this integrand of the double integral, x cubed, is the original integrand we want to compute. Substituting the x equal to x, y equal to y, and z equal to square root of 1 minus x squared minus y squared. This is our parameterization. Substituting this into the pxyz equal x cubed, we obtain the still x cubed. Okay, so this is why this is x cubed, and also we have explained why the Jacobian determinant of yz with respect to uv is this x over square root. Now the remaining work is to compute this double integral. This double integral is b1 x4 square root 1 minus x cubed plus y cubed. of course, we compute this integral using polar coordinate. So in polar coordinate, the r theta corresponding to the B1 is the rectangle r from 0 to 1, theta from 0 to 2 pi, and then this integrand is r cosine theta to the power 4 over square root of 1 minus r square, and then we also have another r come from the Jacobian determinant dr d theta. So this can be 0 2 pi cosine theta 4 d theta 0 1 r to the power 5 square root of 1 minus r square dr. And this can be easily computed. The result is 2 pi over 5. So this is the project integral we are required to compute. And a very interesting feature of project integral, as we know, if f x y z is odd in x, then the surface integral of f x y z and S is symmetric with respect to yz plane. Okay, the integrand is odd in x. The surface is symmetric with respect to xy plane. So without computing, we can confirm that this integral is 0. Okay, because this s can be divided into two parts. One part is on the positive x direction. The surface is divided by two parts, divided into two parts by the yz plane. One part x is positive, the other part x is negative. So both parts, the absolute value of the integral on both parts are the same, because f is odd, and the two parts has the same slope. Okay, so they are the same, but the sign is different. Therefore, adding together, it is 0. So for all the function in x, odd in x function, the surface integral over a surface symmetric with yz plane is 0. However, in this example, the upper hemisphere symmetric with respect to yz plane, of course, and the integrand x cube is odd, but the resulting project integral is not 0. It is 2 pi over 5. So this is a different feature, which is comparing to the surface integral or multiple integral. So I add some remark. In general, if a Jordan domain D in R2 symmetric with respect to yz plane, with respect to y-axis, and fxy equal minus fx minus y, then that is, it is odd in x, then the integral, double integral of f over d is 0. And if D is a three-dimensional domain, symmetric with respect to yz plane, and f(x, y, z) equal minus f minus x, y, z, then this is also 0. And as I said before, if S is a surface symmetric with respect to yz plane, and also f is odd in x, then the surface integral is 0. Okay, this is very useful in computing integral. Okay, but this rule does not apply to project integral or flux integral. Okay, and also here the function is odd with respect to x, and how about it is odd with respect to y and z? So you should answer this question. Also, if it is not odd but even, what will happen? Okay,